This is going to be a geometrical proof of the fundamental theorem of algebra, which is basically going to be an informal version of a proof found in Galois Theory, 3rd edition by Ian Stewart. The fundamental theorem of algebra tells us that for any polynomial f of t with degree greater than or equal to 1 and complex coefficients, there exists at least one complex zero. That is, there'll be at least one complex number z such that f of z is equal to 0. Now, before starting, note that any polynomial f of t with complex coefficients and t some complex number f of t with b sub n not equal to 0 can be written like this. That is, you can factor out the leading coefficient over here, and you can do that by multiplying each of these other terms by b sub n over b sub n. Then you can pull out the b sub n and write this like this. And this polynomial over here is going to have leading coefficient of 1. And the a's here are just the original coefficient divided by b sub n. Then you can call this polynomial p of t, so you can write this original one like this. And you can see from this that if t is such that p is equal to 0, then f is going to be equal to 0. And if t is such that f is equal to 0, then p is going to be equal to 0. So f of t and p of t have the same zeros. So without any loss of generality, you can consider polynomials of this form. So if you're handed a polynomial and the leading coefficient is different than 1, you can factor it out and consider this corresponding polynomial, because both those polynomials will have the same zeros. And over here we're interested in polynomials whose degree is greater than or equal to 1. Now suppose that a sub 0 is equal to 0. Then this term over here is equal to 0, and the polynomial has this form. And you can set this equal to 0, and then you can see that t equals 0 is a solution to this. So t equals 0 is actually a complex zero of this polynomial. So if a sub 0 is equal to 0, this polynomial has at least one complex zero, and so it's consistent with the fundamental theorem of algebra. Now suppose that a sub 0 is not equal to 0. In order to deal with that case, I'm going to start with some definitions. I'm going to let c sub epsilon of theta be equal to r sub epsilon times e to the I theta, with r defined as this, and epsilon ranging from 0 up to 1. So that if epsilon is equal to 0, r is going to be equal to 0. And as epsilon tends towards 1, r will tend towards infinity. So if I fix a value of epsilon, I fix the value of r. And if this is fixed, this equation here is just the equation of a parameterized circle. And if I choose a value of theta, that's just going to be a point on the circle. And if I let theta increase by 2 pi, the point will just move around and come back to where it started. Now, if I consider all the values of epsilon, what I've done is I've defined a family of parameterized circles that cover the entire plane as epsilon goes from 0 to 1. So notice that if epsilon is equal to 0, c sub epsilon, which will be c sub 0, is just going to be equal to 0 since this is 0. So for epsilon equal to 0, the circle is just the point at the origin. And then as you increase epsilon, the point will split into a circle, and the circle will tend towards infinity. So the family of circles covers every point in the complex plane. Now I'm going to define an alpha of t equal to p of t over magnitude of t raised to the n plus 1, with p defined as above. And you can see from this that if p is such that if p is 0, you're going to have 0 over something non-zero. So alpha is 0. So if p is 0, then alpha is 0. And if alpha is 0, you have a function here over something non-zero, so that function has to be 0. So if alpha is 0, then p is 0. And now I'm going to let t be equal to a point on one of the circles, and I'm going to substitute this expression for t into this equation. So alpha of t becomes this, and p of t becomes this, and the magnitude of t is just the magnitude of this, which is the magnitude of this, and the magnitude of a point on a circle is just the radius of the circle. So magnitude of t becomes r sub epsilon, and the denominator, this denominator becomes this. Now you can see from looking at this function that alpha is dependent on epsilon and theta, here, here, and here. So I can define a gamma sub epsilon of theta equal to this alpha, which is equal to this, and then I get this equation over here. And for a fixed value of epsilon, gamma is actually a closed loop in the complex plane. If epsilon is fixed, then r is going to be fixed. And if I choose a point theta, I've chosen a point on a particular circle. Now gamma is going to have a value dependent on that particular point. Now if I let theta increase by 2 pi, that point is going to move around and come back to where it started. So the value of gamma is going to come back to its original value, and gamma will form a closed loop. So for fixed epsilon, gamma sub epsilon of theta maps the circle c sub epsilon onto a closed loop gamma sub epsilon. So altogether, what we have is this. Our family of parameterized circles with r defined like this, with epsilon ranging from 0 up to 1, with p defined as it was above, and the degree of p being greater than or equal to 1, and t being equal to a point on one of the circles, and our definition of gamma from above. And you can see from this that if p is 0, then gamma is going to be equal to 0. So if p is 0, then gamma is 0, and if gamma is 0, then p is 0. So if this is 0, then this is 0. Now I'm going to look at the behavior of gamma as a function of epsilon. First, let epsilon equal to 0. If epsilon is equal to 0, then r is going to be equal to 0. So you have r sub 0 is equal to 0, and since t is equal to this, and r sub epsilon is equal to r sub 0, and r sub 0 is 0, we have t equal to 0. So p of t, with t in this form, is the same as p of 0, and p of 0 is going to be equal to a0, because if I plug 0 into this equation, I just get a0. So gamma sub 0 of theta is going to be p, which is just a0 now, over r sub epsilon, which is r sub 0, which is 0. So you have 0 raised to the n, which is 0 plus 1. So gamma sub 0 is going to be equal to a sub 0. So gamma is now going to map the point t equal to 0 in the t-plane over to the point a0 in the gamma plane. Now what happens if I increase epsilon by a very small amount, so that epsilon is a very small positive number? Then r is going to be a very small number, and t is going to be a point on a circle of very small radius. So now gamma is going to take a point on that circle, corresponding to some fixed value of theta, over to a point in the gamma plane. And that point is going to be close to this point. And that's because this point is close to this point, and a0 is from this point. So these 2 points are close together, and the function gamma is continuous. So these 2 points are going to be close together. Now if I let theta increase by 2 pi, this point is going to move around the circle and come back. And this corresponding point is going to move around some closed loop and come back to its original value. And all the points on this loop are going to be close to the point A0. And that's because all the points on this circle are close to the origin. And of course, A0 is from the origin. And the function gamma is continuous. Now what happens as epsilon approaches 1? Here's our definition of gamma from above, with p defined like this, and t being equal to a point on one of the circles. And what I'm going to do is I'm going to substitute this expression for p into here with t equal to this. So the first term is going to be this raised to the n, which is over here. Then I'm going to have a sub n minus 1 over here. That's going to be raised to the, and that's going to be times t raised to this, but t is this. So I'm going to have this expression here to the n minus 1 plus the additional terms. Now what I'm going to do is just distribute the exponent. I'm going to distribute the exponents in these terms. So this term over here is going to become r sub epsilon to the n over here, and that'll be times e to the I n theta over here, and then I'm going to have a sub n minus 1 over here, and that'll be times r sub epsilon to the n minus 1 over here, and that'll be times e to the I n minus 1 theta over here, plus all these additional terms. Now what I'd like to do is I'd like to split the numerator into two parts. I'd like to group all these terms together and then just divide the denominator into the first term and the denominator into this term. So if I divide the denominator into the first term, what I'll do is I'll write it as r sub epsilon to the n over here divided by this times this factor e to the I n theta. And then I'll just divide this into this and get this term over here. Now, what happens as epsilon approaches 1? As epsilon approaches 1, r is going to approach infinity. So this term over here is actually going to approach 1, and that's because as r gets very large, I can drop this 1 over here. As r gets very large, I can drop this 1 over here, and then I'm just going to have r sub epsilon to the n over r sub epsilon to the n, which is just 1. And this term is going to approach 0, and that's because all the powers of r in the numerator are less than the power of r in the denominator. And if you like, what you can do is you could divide the denominator into each of these terms, and then you'll get factors of r raised to some power over this. And the first one of those will be this over this, which is written over here. So as r tends towards infinity, you can drop the 1 over here, and this denominator just becomes this. Then you can split the numerator up algebraically, so you'll have r sub epsilon to the n times r to the minus 1. And these two terms will cancel, and you'll get r sub epsilon to the minus 1, which is just 1 over r sub epsilon. And as r approaches infinity, that term is going to approach 0. And all the other terms, all the other factors of r raised to a power over this will also approach 0. So this whole thing will approach 0. So as epsilon approaches 1, gamma sub epsilon is going to approach this factor over here. So the limit as epsilon approaches 1 of gamma sub epsilon of theta is just going to be equal to e to the I n theta. And e to the I n theta is just a unit circle. in the gamma plane, which is going to wrap around n times as theta goes from 0 to 2 pi. So I'm going to define gamma sub 1 of theta to be equal to e to the in theta. So what's going on when epsilon is equal to 1 is that you'll have a circle at infinity in the t-plane, and gamma is going to map that onto a unit circle in the gamma plane. And as theta goes from 0 to 2 pi in this plane, this point over here is going to wrap around n times and come back to the starting point. So altogether, what's going on is that when you have epsilon equal to 0, gamma maps that point to this point a sub 0. And when epsilon increases a little bit, that point splits into a circle, and gamma maps that circle onto a closed loop, which is near this point. But then as epsilon tends towards 1, this circle is going to tend towards infinity, and this loop over here is going to converge to a unit circle over here. And during that process, this loop has got to pass through the origin at least one time. And when that loop passes through the origin, gamma is going to be equal to 0. And when gamma is 0, then p is 0. So for epsilon equal to 0, you're over here. And for epsilon equal to 1, you're over here. So for at least one value of epsilon between 0 and 1, you're going to have a loop that passes through the origin. And corresponding to that value of epsilon, you're going to have a circle in this plane over here that maps to that loop. And the point on that circle that maps to the origin, where p is equal to 0, is going to be a 0 of the polynomial. And there might be more than one of those points on a given circle. So to start with, t is equal to 0, and then t splits into a circle, and then that circle tends towards infinity. And during that process, p is actually sampling every point in the complex plane, and you find that at least one of those points is a 0 of the polynomial p. So to sum this up, for a0 not equal to 0, the loop gamma sub epsilon must pass through the origin where gamma sub epsilon of theta is equal to 0 at least once. And that'll be for some fixed value of epsilon between 0 and 1. And when that happens, you have this condition over here, gamma sub epsilon of theta is equal to 0. And when you have that condition, you have p being equal to 0. So the corresponding value of t from over here is going to be a 0 of p of t.